spent some toudai for a while. Alright, so thanks a lot for your attention. Questions? This might not be completely fair. It might be more appropriate for your experimental colleagues, but a couple of times you mentioned how clean the surfaces were from the focused ion beam, and I was wondering how was that quantified? And secondly, kind of what's at stake? How sensitive are these sorts of effects to weak disorder that's almost certainly at the surface? Despite these efforts. Right. So I have a kind of indirect answer, which is that since you're seeing some surface component of the quantum oscillation, you know that at least the portion of the orbit that's on the surface is clean enough that you can complete it without scattering. And so since you see these nice clean quantum oscillations, that's indicative of having a very clean surface. It's hard to extract, say, what's exactly the transport, what's the mean free path of the surface, since the bulk is also conducting. But I think there's a really good sign that the surfaces are morally clean in the sense that cyclotron frequency times the scattering rate is large, at a few Tesla. I was curious if your collaborators have done some sort of characterization of the surfaces. Yeah, I believe they have, but I can't speak to the details. I mean, they know how thick the ion implantation layers are and things like that. So.
I have a question. So I'm having a bit of a difficulty maybe understanding when you tilt the field, how does this bulk transport work? Because it seems that once you tilt the field, real space, electrons spin at an angle. Right?
Yeah, precisely.
So does that affect the outcome?
Yeah, so the chiral lambda level goes along the magnetic field, just as we say. And so if I tilt the field around to the surface, it has to go further through the bulk. And so actually you expect the scattering to become more and more detrimental the longer you make this orbit. And indeed, actually they see that as they tilt the surface, the amplitude, the magnetic field, the amplitude of the surface oscillation dies pretty quickly. So it's only observable within some 30 degrees of the top surface. So it's kind of consistent with what you expect.
Other question? Just to get a clarification, what does determine the frequency of the surface components of the oscillation? You said something like if you're right at the wild point in the bulk.
Yeah. So it's always arc length over, the frequency in the magnetic field. Yeah, it's basically the area difference between the zero doping and whatever doping you're at of this arc length.
What happens at zero doping then?
Yeah, so at zero doping, everything's particle Hopf symmetric. So as you adjust the magnetic field, the lambda levels move away from the chemical potential, and they never cross the chemical potential. So you won't see this quantum oscillation. You still have these orbits, but they're just moving away from you symmetrically in a particle Hopf symmetric fashion. So you need levels to keep crossing your chemical potential to see this quantum oscillation. Yeah, so you need some finite doping, actually.
Any other questions?
In derived semimetals with fermions, there are two closed orbits that can form. One is only on the surface, the other one goes through the bulk.
Yeah.
So do you understand which will give rise to stronger quantum oscillations?
So that's dependent on probably many details. Like I would assume that the surface only has a shorter orbit, so has less chance to scatter. That sounds a bit more robust to disorder.
At the surface, there's a kink where the two fermions connect, so it's hard to scatter from one to the other too.
So are you asking if you have this arc-like termination? So there's two possible terminations. One is where you have arcs, and one is where you have like a TI surface.
Yeah, so here
What
the
you're
wax
asking?
semiconductor. Yeah.
This is
Then
for
there are,
your
yeah. So then there are two fermions on each surface. And where they connect, generically there is a kink. It's not a smooth connection. So it's hard to hop from one fermion to the other one. It's also hard to go through the bulk. So just wondering which process.
Sorry, I don't understand why is it hard to go through the bulk?
Well, because there's a thickness. As the film gets thicker and thicker, it's harder to go through.
But it's not harder to go into it, right? If it's thicker, you may scatter before you get all the way through. But you always go into the bulk.
Yeah, that's what I meant. It's harder to go all the way for thicker. So yeah.
Well, maybe we can discuss after. I'm not quite. I feel like I'm missing something important.
So I want to follow up on that point there. When you look at the two that you're after from metal, when you have the two arms, so it's like the plus and minus of one arm. Then can have to go through the bulk and come back. Then the negative and positive of the other one is an opposite channel of the solution. So it's not like you go from one arm to the other arm.
Right. You have two separate copies of this Y orbit in the ideal situation that don't talk to each other, basically. Yeah.
From surface to bulk back. One is the other arm is the other.
Yes, precisely. Yeah. Thank you.
So this wild system has finite doping, so the bulk, you have a bulk fermicillium as well, right? So then once you're considering this quantum oscillation of the arc, the electron will go from firstly on the surface on the arc, then it will go to it's possible for this electron to go to the bulk Fermi surface. Then it's circling around the bulk Fermi surface, but it can circle for many times before it runs into the other surface.
Yeah, so I don't think this actually happens. There's some topological connection between this bulk chiral Landau level and the surface arc, and the surface doesn't go into these non-chiral Landau levels, it goes straight into the bulk one. So unless you scatter, this process where you kind of circle many times.
So the point is the first circle many times is very difficult to estimate how much time it spent on this circling on the bulk Fermi surface.
But as I said, unless you have impurity scattering, this won't occur. You go straight through into this chiral mode instead.
Okay, if there's no more questions. Oh, there's one question.
It kind of seemed like it was important to be able to follow the orbit of so you are along the arc and then you go through the bulk. So in the bulk the bands would be less well defined than they are at the surface.
In what sense?
Well, so at the surface, it's kind of a nice picture, but you have the well-defined space, or linear dispersing space. And then, at least in the pictures that you and did here, you were following your surface space, which then went into the bulk and then back up into the other vial point. So when you're inside this, or you're inside, together with the other band, can you really say that you're staying on that same band?
Yeah, this is kind of topological argument that I gave. So that the bulk chiral Landau level has to be able to turn around, and the only way it can do this is through this surface arc. And so they're actually turned into this state when you turn on a magnetic field.
And so you really have some well-defined connection between the surface arc and the bulk chiral lambda level, not the non-chiral one. It's related to the chief question. But the bulk bands are well-defined in the clean. Okay, under ideal conditions, in the clean case, so clean enough to see bulk quantum oscillations, you have these nice separate bulk lambda levels, and they're very well-defined. Just the chiral one connects to the surface space. The other ones can turn around just by scattering off the surface on their own. And you actually see exactly this if you just put this problem on a computer and find the exact eigenspace. So the semi-classic picture I gave was just the simplest way to understand it, but you can also confirm this directly numerically with further.
Even with weak interactions, I guess.
Yeah, so interactions are probably not very important at low temperatures because the scattering rate for these electrons will go down at some kind of t-squared if you have some doping. So if you're cool enough, I think you can, and these are weakly correlated materials, so I think you can probably ignore dephasing from an interaction.
I think we have exhausted all the questions, so let's thank the speaker again. And we will reconvene here at 11.
Okay, thank you. I'd like to first thank the organizers for having me to do this talk, and this is work that I did back when I was at the University of Toronto with me on keys, and Eric you just saw. I'm at the University of Waterloo now, so this is about a generic spin model for the honeycomb iridates, including some effects of kernel distortion. So today you've heard a lot about honeycomb iridates, so I'm going to go very, very quickly through my first sort of introductory slide. So you've seen this cadet model a lot, and so I'm not going to try to convince you that it's interesting right now. And again, we know that these are built from these gay effective half states. You know, they're strongly spin orbit entangled wave functions that give rise to interesting anisotropic physics. And again, there's this lovely proposal from Kelly and Balloon, where they showed that if you had edge-shared octahedra and you only had oxygen popping, you could generate this coupling in a real solid-state system. One thing I just want to point out for future use is that when you do this, it comes out negative. So I'm going to call this ferromagnetic coupling. And again, very, very quickly, you can, in principle, realize this type of physics in these honeycomb iridates through the sodium iridium oxide and the alpha lithium oxide. Okay, well, do that again. So we know that they're not spinless. Right? We know they order magnetically. This is a zigzag pattern for the sodium, and for the alpha lithium, some indications of spiral order. Again, there's no definite statement on that just yet. So, what else do we know about this order? Well, you might think that if we see this thing order, you might have gotten spin liquid physics completely.
K1, K2 model, apparently it's kind of new, interesting quantum/classical model, and the reason we studied this model was motivated by experimentalists. So let me first start by acknowledging my collaborators. So this work, which I'm going to talk about, is mostly done with Ioannis Hatzakis, who is now in University of Minnesota, and Craig Price, who is in Penn State, and some previous results were obtained with Yuri Tuduk, who is my PhD student, and Peter Boyce. And I also acknowledge collaboration with FRG guides, Stefan Rachel, Johannes Reuter, and Ronnie Damari, who did the FRG study of this K1, K2 model. So here is the outline of my talk. So I will start with motivations why we decided to study this model, and I will advocate also the importance of second neighbor T-type interaction